Every single day, the sun sends more energy to the surface of the Earth than the entire human population uses in a year. Every single day, and for most of human history, we had absolutely no way to capture it. Then solar panels came along, and one company figured out how to build them better, faster, and more efficiently than anyone else on the planet. That company is Jinko Solar. They are currently the largest solar panel manufacturer in the world, shipping panels to over 180 countries, and the technology inside every panel they produce starts its life as one of the most ordinary materials you can find anywhere on Earth: sand. The process begins with silicon. Silicon is extracted from quartz sand through a high-temperature smelting process, where the sand gets heated in a furnace to over 1700 degrees Celsius with carbon material. At that temperature, a chemical reaction strips the oxygen away from the silicon dioxide in the sand and leaves behind raw silicon. But this raw silicon is not pure enough for solar panels. It contains tiny amounts of impurities that would dramatically reduce the efficiency of the final cell. So it goes through a purification process called the Siemens process, where the silicon gets converted into a gas, purified through a series of chemical reactions, and then converted back into solid silicon. The result is polysilicon, with a purity level of 99.9%. 9 nines of purity. At that level of purity, you could have 10 billion silicon atoms, and fewer than one of them would be an impurity. That ultra-pure polysilicon then goes into one of the most impressive machines in the entire factory: a Czochralski crystal growing furnace. Inside this furnace, the polysilicon gets melted back down into liquid form at around 14-15 degrees Celsius, and a small seed crystal of silicon gets lowered into the molten surface. Then the seed crystal gets slowly pulled upward while rotating, and as it rises, the molten silicon solidifies onto it, growing a perfect single crystal cylinder called an ingot. This process takes between 20 and 40 hours, depending on the size of the ingot being grown. The pulling speed and rotation rate are controlled by computer to within fractions of a millimeter per minute, because if either variable drifts even slightly, the crystal structure of the growing ingot becomes irregular, and the electrical performance of every cell made from it drops. The finished ingot comes out of the furnace as a large cylindrical rod of single crystal silicon that can be over a meter long and weigh 30 kilograms. It gets inspected for crystal quality and then loaded into a wire saw machine. This machine cuts the ingot into wafers using a web of extremely fine wire coated with an abrasive slurry that moves at high speed across the ingot surface. The wire is so fine it is barely thicker than a human hair, and the cuts it makes produce wafers that are only 160 to 180 micrometers thick. That is thinner than 2 sheets of printer paper stacked together. The wire saw can cut hundreds of wafers from a single ingot simultaneously, and the entire cutting process is computer controlled to keep every wafer at a consistent thickness across its entire surface. After cutting, every wafer goes through a cleaning and texturing process. The surface of a freshly cut silicon wafer is actually quite reflective, and a reflective surface is the enemy of a solar cell, because any light that bounces off the surface is light that never gets converted into electricity. So, the wafers go through a chemical etching bath, where a precisely controlled solution creates a microscopic pyramid texture across the entire surface. These tiny pyramids, invisible to the naked eye, act as light traps. When light hits the angled surface of a pyramid, it gets redirected at an angle that takes it deeper into the silicon, rather than bouncing it back out. This texturing process alone can increase the light absorption of the wafer by over 30% compared to a flat surface. Now the wafer needs to become a cell that actually generates electricity. This happens in a process called diffusion doping. The wafers travel through a tube furnace where they get exposed to phosphorus gas at around 800 degrees Celsius. The phosphorus atoms diffuse into the surface layer of the silicon, creating what is called a PN junction. This junction is the heart of the solar cell. It is the boundary between 2 different types of silicon, one with extra electrons and one with a deficit of electrons. When photons from sunlight hit this junction, they knock electrons loose, and the built-in electric field at the junction pushes those electrons in one direction, creating an electric current. Without this junction, the wafer is just a piece of silicon. With it, the wafer becomes a device that converts light directly into electricity. After doping, the cells go through an anti-reflection coating process. A thin layer of silicon nitride gets deposited onto the front surface of each cell using a plasma-enhanced chemical vapor deposition machine. This layer is only about 80 nanometers thick, which is roughly 1,000th the thickness of a human hair, but it performs two critical functions simultaneously. It dramatically reduces the amount of light reflected off the cell surface, pushing absorption even higher than the pyramid texturing alone achieves. And it passivates the surface of the silicon, meaning it neutralizes defects on the cell surface that would otherwise capture electrons and reduce the current output. The blue or black color you see on finished solar panels comes entirely from this coating. Next comes screen printing. This is the step where the metal contact grid gets applied to the surface of the cell, the thin silver lines you can see running across the front of a solar panel. A screen printing machine forces a silver paste through a fine mesh screen onto the front surface of the cell in a precise grid pattern, then applies an aluminium paste to the full back surface. These metal contacts are what collect the electrons that the junction knocks loose and channel them out of the cell as usable electrical current. After printing, every cell goes through a firing furnace at around 800 degrees Celsius, where the metal pastes burn through the anti-reflection coating at the contact points and form a direct electrical connection to the silicon beneath. The firing profile, the exact temperature curve the cells travel through, has to be controlled to within a few degrees, because too hot and the metal penetrates too deep into the silicon and short circuits the junction. Too cool and the contact resistance is too high and the cell loses efficiency. Every finished cell then goes through an automated electrical test on a flash tester. A xenon flash lamp fires a pulse of light at a standardized intensity onto the cell surface for a fraction of a second, while probes contact the metal connections and measure the electrical output. The machine records the peak power output, the voltage, the current, and the efficiency of every single cell, and sorts them automatically into efficiency bins. Cells are matched by bin when they get assembled into panels, because a panel made from cells with mismatched electrical characteristics performs worse than any of the individual cells would suggest, as the weakest cell limits the output of every cell in the string it is connected to. The sorted cells then move to the panel assembly line. A precision tabbing and stringing machine picks up individual cells and solders copper ribbon conductors between them, connecting them in series strings. The soldering happens with exactly controlled heat and pressure to form reliable joints without cracking the wafers, which despite being made of silicon, are actually quite brittle at this thickness. The strings of cells then get laid out on a sheet of low iron tempered glass. Low iron glass is used because standard glass has a greenish tint from its iron content that reduces light transmission. Low iron glass is optically clearer and allows more light to reach the cells. Between the cells and the glass sits a layer of encapsulant film, a polymer material that bonds everything together and protects the cells from moisture, vibration, and mechanical stress. A second layer of encapsulant goes over the back of the cell strings, followed by a weatherproof backsheet. This complete assembly goes into a lamination machine where heat and vacuum pressure are applied simultaneously. The heat melts and flows the encapsulant film around every cell and every conductor, completely encapsulating the entire electrical assembly in a solid polymer matrix. The vacuum removes every air bubble before the encapsulant cures, because any air pocket left in the laminate becomes a site where moisture can eventually penetrate and cause cell degradation. After lamination, the panel gets its aluminium frame fitted. The junction box gets bonded to the back and the electrical connections get made inside it. And the finished panel goes through a final flash test to verify the complete assembly performs at its rated output. Jinko Solar produces enough panels every single year to power tens of millions of homes. The machines inside their factories run around the clock, and the quality control systems reject any panel that does not meet specification before it ever leaves the building. What starts as ordinary sand becomes, after this entire extraordinary process, a panel that will sit on a rooftop and silently convert sunlight into electricity every single day for the next 25 to 30 years, without a single moving part, without any fuel, and without producing a single gram of emissions during operation. That is not just impressive manufacturing, that is one of the most important things being built in any factory anywhere in the world right now.